Okay, we are NAU Motor Systems, and we are set out to design a motor controller for electric vehicles. We've got Dan Eichenberger, Jeremy King, Christine Coleman, and myself, Nick McGregor. All right, we'll be going over our sponsor, Electric Blue, our wonderful team advisor, Dr. Kipple. We'll cover our problem statement and the requirements and specifications associated with that, as well as the design that we've decided so far, and the path we've chosen to take. We'll also go over the activities that we have planned throughout February and our budget and the money we've spent so far. Our sponsor is Electric Blue Motors. They were unable to join us. They're probably just running late. But the vice president is Bill Schlanger and the president is Dave LeBeau. And what they do is they convert vehicles from gas to electric. And they also design electric vehicle components for these vehicles.
As Nick said, our team advisor this year is Dr. Kipple. She's an E professor up here. She was with us last year as a professor when we started our initial controller design of 386 class. And we put this picture up here of her because we pretty much think it's the coolest one on the E faculty. So this is Dr. Kipple when she was down at Fort Huachuca. I'm not too sure what she's standing on, but it's got the Apache in the background. Our problem today, our motor controllers today. When Electric Blue came to us, they said, we want you guys to build us a cheaper one. So that's our main thing. And when I say cheaper, I just mean lower in cost. Because today's are expensive, they're out of date, and because they're out of date, they use older components that make the motor controllers larger in size. So our goal is to basically do everything now. So we want to make it cheaper for Electric Blue to build and put into their cars. We want to make them smaller in size, and to make them smaller in size, we need to use newer components. Electric vehicles have three main parts. You have your batteries, which is your fuel source, equivalent to like in a gas-powered motor, which is like gasoline in a gas tank. Then you have your motor, which converts the electric energy from the batteries to kinetic energy, which is then going to move the car down the road. Then you have your motor controller, which is placed between the batteries and the motor. And the motor controller controls the power which is sent to the motor, so thus we can control the speed of the motor. For our testing purposes, this is where the Land Rover is going to come into play that you saw at the beginning. Nick had purchased it a year or so ago, and the idea to turn it into an electric vehicle. We're going to use this vehicle to test everyday applications or situations with everyday driving in the city. The requirements and specification for our project, the electrical side of it, the controller needs to have an operational range of 96 volts to 144 volts. And the controller itself needs to handle a minimum of 500 amps. For environmental conditions, the controller needs to withstand, like I said, everyday driving, whether you hit a speed bump, a pothole, have to brake fast, different weather conditions, whether it's freezing temperatures to hot temperatures, to humidity, dry situations. And the general requirements are, obviously, like we said, we need it to be a cheaper controller, so we've got to have it less than the controllers that are out on the market today. We want it to, if the controller somewhat fails, we want it to fail in a known and safe state, therefore shutting off all the power to the motor instead of sending it all the power to the motor, and basically you just have to wait until the batteries die before it will stop, which wouldn't be a good thing. So. And then the controller itself should not emit any hazardous radiation that could be harmful to humans. And take it over there.
Here we have a basic block diagram schematic of our motor controller when we connect to a motor. We have the 144 volt power source, which will be coming from our batteries. We have a DC brush motor, and between that and here ground we have the MOSFET, which controls turning off and on the motor itself. We have the MOSFET driver, which controls the MOSFET. We have our pulse width modulation chip, which will output a modulated signal for the MOSFET driver. We have a frequency set potentiometer, which is used to set the frequency of our pulse width modulation chip. We have a 0 to 5K throttle potentiometer, which basically, this acts as a gas pedal to control the speed of the motor itself. And in our system, we needed two extra voltage sources, a 12 volt and a 5 volt, to power our chips. Here is our design decision matrix, and we have two general decisions basically to go from. We can either use a pulse width modulation chip or a microcontroller. And with each selection, you can either have 4 MOSFETs and 4 drivers, or 1 MOSFET and 1 driver. And as you can see here, the pulse width modulation with 4 MOSFETs and 4 driver has basically taken the cake on this. And the most important factors for us were size, power, cost, reliability, and environmental. Reliability is the most important, as with what Jeremy said, that if our motor controller fails, we want it to fail in a known state, because the safety of our drivers and those around is the most important. And cost is the second most important, because the idea of our project is to build a low-cost, efficient motor controller. So here's just kind of a breakdown of some of the parts we have chosen so far. We have chosen this MOSFET and MOSFET driver combination from our research to be the best for our application. We are using the standard 5K throttle potentiometer. We are using 12-volt AGM batteries. We would like to purchase this battery charger. Of course, it's a little expensive, so we're hoping to work that out. We are going with a 9-inch DC brush motor to move our vehicle. And for the remaining research we have left, we need to do a little bit of research on diodes, basically to prevent latch-up in our system, or in our motor controller design. We also need to work on car suspension. With the batteries we have, they're pretty heavy, and the weight distribution has basically offset, because we're putting most of the batteries in the rear, and so we need to compensate this suspension so that the car will drive safely. And as Jeremy spoke, we need to do our testing procedures to test it in environmental conditions. That's all, Christine.
I'm doing the budget, and basically we broke it down into a pie chart because it was easier to see than the actual table that we had. So we have our battery box fabrication, we have our battery charger, the high voltage components, your motor, the actual motor controller, marketing and our sponsors, motor mounting and miscellaneous. And we had a grant from NAU/APS. So we broke it down based on how much we got for the grant. And the most expensive thing right now that we have is the battery charger, which is about $2,000. That's how much it's going to cost us as of right now. And then planned activities through February. So we have I broke it down into batteries, our website, the car, papers, and our motor controller. And the motor controller is red because that's the main part of our project. The rest is basically for the test vehicle and pieces for the capstone class. But the batteries, as of right now, we have some of the battery boxes inside of the car. We also have the motor painted and ready to put in. And let's see what else. We also have part of the prototype already finished, so we're on track with that. And then this is the spending and hours through February. So far we've spent a little bit of money to fix up the motor and to build the actual battery boxes. But we should spend about $2,500 left on the car up through February, and then about $500 on the motor controller itself. And then we allocated about 12 hours for the papers, 4 hours for the presentation, based on the information we had from our individual memos that we did for Dr. Scott. And then we estimated about 36 hours for the car and 48 hours for the motor controller, also based off of that information. And then the website should take about 30 more hours to have it fully up and running.